Alright, we need to get started. There's one announcement that I was asked to make about AMSA, American Medical Student Association, has their second meeting tomorrow in Agnes Arnold. And then there's some other things in here that you probably won't be able to see very well on the screen, but I've been asked by one of your classmates to share some information about volunteer and internship opportunities at Ronald McDonald House. So this information will be in the notes for you to take a look at. There's a lot of stuff in there, so I can't go through all of it, but this is information about those opportunities at Ronald McDonald House over in the medical center. So that would be something you're interested in, especially if you're aspiring to a career in medicine. So they have volunteer programs, which are throughout the year, and they also have an internship program available. All right, so the first exam is finishing up today. This is, I'm trying to shrink this a little bit if it lets me. Alright, well, anyway, we'll deal with that. So the exam is finishing up today. Many of you have asked if you're able to go through your results. They should be opened up tonight after everyone finishes. I'll double check to make sure that it's set up to do that. So you can review what you missed. If you want to go over it with me, we can certainly do that sometime in my office. And if you're not happy with your score, then we can talk about ways to improve that in the future. So it's just the first exam. We have a lot of time left. And so we'll try to make improvements in the future if you're not happy with where you are now. So today we're going to talk about the last section of Chapter 4, which is molecular orbital theory. MO theory as it's often abbreviated. Zoom out a little bit. There we go. Okay, so we're going to talk about MO theory, which is the end of Chapter 4. It's the last type of bonding theory we're going to deal with. So last time we introduced valence bond theory, which is the idea that when atoms form covalent bonds, you have overlap of atomic or hybrid orbitals or some combination of those two to form those bonds, but it's very much a localized bonding approach. It's taking the stance that you have individual orbitals on each atom, the hybrid orbitals being on the central atom, and then those individual orbitals are overlapping with each other. But we're going to talk today about a different bonding theory that it turns out is much more accurate, although much more complicated. So we're not only going to deal with it for relatively simple species, and that's called molecular orbital theory. Now, you might be asking the question, why do we need another theory? Because for many things, valence bond theory and hybridization works quite well. And you'll see that when you take organic chemistry, if you go on that far to take organic chemistry, the ideas of hybridization are still very important in that field and still used today. So the question is, what's the point of having another more complicated bonding theory? And it's because in some cases this valence bond theory doesn't quite predict exactly what's going on in these molecules. So if we start with a very simple molecule, O2, so valence bond theory, we can draw a Lewis structure to predict the bonding and the arrangement of the electrons. And so what we would get for O2 is this. We'd have a double bond, and we'd have two lone pairs on each of these oxygen atoms there. And as we said last time, you can predict that the bonding type for this would be 1 sigma and 1 pi. All right, whenever you have a double bond, valence bond theory predicts that one of those bonds will be sigma, the other one will be pi. And so that's all the stuff we learned last time. And valence bond theory also commonly predicts, and as long as you have an even number of electrons, that all of those electrons will be paired up. So we see that that's the case in oxygen. That's the case in 99.9% of the Lewis structures we ask you to draw. All of the electrons are showed as paired. So in this description, we would predict that there's 0 unpaired electrons. Now, something we're going to talk a little bit more in detail about today, we haven't introduced it yet in this course, is what are called magnetic properties. So when you have different numbers of paired or unpaired electrons, those are going to influence how those molecules behave in a magnetic field. So if in a situation where you have all of your electrons paired, that means 0 unpaired electrons, we call that diamagnetic. So the valence bond picture of O2 predicts that all of the electrons are paired, which means that we would call it diamagnetic. And in terms of the behavior in a magnetic field, it has a very weak interaction with the magnetic field, but it's going to be weakly repelled by that field. Have you ever, if you're ever seen the video online where someone levitated a frog in a very strong magnetic field, And that's because living tissue is mostly made up of diamagnetic things, and so if you put those into a really strong magnetic field, they will be repelled by that field and they can be levitated. I don't think there's a strong enough magnetic field to levitate a person, but for something really small like a frog, you can do that. But this is all what we predict for O2 using valence bond theory, but let's see what actually happens. Let's go do a quick experiment. Alright, so that's what we have here. We're going to see what happens. So what this guy is going to do is he's going to take two liquid samples. One is going to be liquid nitrogen, one is going to be liquid oxygen, and he's going to introduce them to this strong magnetic field and see what happens to them. Now, as we talked about, the valence bond theory predicts that O2 is diamagnetic, which means the prediction is that O2 should be weakly repelled by this field, not really have any interaction with it. And so let's see what happens when he does this. I forget which one he's starting with. This is oxygen. So as you can see, liquid oxygen is held between the magnets, which would suggest that it's actually attracted to the magnetic field. So you can see that the liquid is held in place. It does evaporate quickly because it has a very low boiling point, but while it's still liquid form, it stays there and is interacting with magnetic fields in a way that you would not predict it to happen, because if it was diamagnetic, it should go right through. And I think he's going to show that next if we get to... they're pausing for dramatic effect and probably saying some things that we can't hear right now. But they're going to go, and I think the next thing they're going to do, if I remember this video correctly, is they're going to do liquid nitrogen. So another diatomic gas that's in a liquid state in this case, and they're going to pour liquid nitrogen through. And you can see the woman on your right has liquid nitrogen. So there's oxygen, it sticks in between the magnets. And then when she does nitrogen, if she does it again, I don't know, the nitrogen goes straight through. We can clearly see a difference in the behavior between oxygen and nitrogen, and also that this prediction that we had about the diamagnetism of oxygen is quite clearly not correct. And so, as always is the case in science, if you have a prediction and then your prediction is not met by experimental observation, that means you must be wrong about something. So what we saw in that video is that O2 is actually paramagnetic. Okay, so valence bond theory, while it predicts some of the key properties of these molecules correctly, it's not always perfect, and in this case we see that valence bond theory does not correctly predict the magnetism of O2. So how do we rationalize the fact that there are actually unpaired electrons in O2, and that it is paramagnetic and not diamagnetic? And that's what this bonding theory we're going to introduce today is going to allow us to do. Alright, so what we're going to talk about today is called molecular orbital theory. And so we want to understand some of the basic principles and concepts that are associated with this. Now there is some similarity between what we're doing today and what we did last time, but this time we're going to form delocalized orbitals. So we're still going to mix atomic orbitals, and remember that these atomic orbitals are actually mathematical wave functions. So we're going to mathematically combine them. And we're going to do what's called linear combinations. Which means we're going to add and subtract those wave functions. And the key difference, though, between molecular orbital theory and valence bond theory is that we're going to form delocalized molecular orbitals. Alright, in valence bond theory that we talked about last time, we said that there's an orbital on one atom, an orbital on another atom, and they come together and overlap. What we're doing in molecular orbital theory is we're mathematically combining the atomic wave functions to form new orbitals that are delocalized over the entire molecule. And it's not that you have two separate orbitals that belong to one oxygen and the other in the case of O2, but it's that you have new orbitals that are delocalized over the entire O2 molecule. So there is a slight distinction there in the theoretical treatment that is very important practically. Now, in terms of the energy, which orbitals are able to mix together? So we have, on each of our atoms that we're going to combine to form molecules, we have a number of atomic orbitals available. And really the only ones that mix together are those that are close in energy. Alright, so we talked about the energy ordering of atomic orbitals in the context of electron configurations and other things that we dealt with in Chapter 3. And so when we're mixing those atomic orbitals to make molecular orbitals, the two that we're mixing together have to be close enough in energy to be able to mix. You can't just mix any random two atomic orbitals. And we'll see how that works a little bit later. And then which atomic orbitals do we even care about? Just like any other bonding theory, the only ones that really matter are the valence orbitals. Alright, so those core orbitals that are really close to the nucleus, they're not really able to mix very well anyway. They're always going to be completely occupied in these orbital diagrams that we're going to generate. So we don't really care about them. We only care about the valence orbitals, just like we would for the simpler bonding theories that we started with. Alright, so when we mix atomic orbitals together, as I said, we're going to do linear combinations of atomic orbitals. And so whenever you take two atomic orbitals and mix them, you're going to get two molecular orbitals. So there's always a conservation of orbitals if you want to think about it that way. Whenever we mix two orbitals, we get two molecular orbitals. If we mix more than two, we'll get that same number of molecular orbitals out. But in the simplest sense, where we're just mixing together two orbitals, we're going to get a bonding and an antibonding orbital. So each time we mix two together, we get one of each, one bonding, one antibonding. And so what the wave function looks like for this is, as I said, these are linear combinations of atomic orbitals, and the wave function for a bonding orbital is going to be an additive sum of the two. So we have two atomic orbitals we're mixing together, and we're just going to add them in phase, as we would say, when they both have the same sign. So this is an additive combination. Right? And then the antibonding orbital is the opposite. So if we're mixing two orbitals together, the antibonding combination is just a subtractive combination of those two, which means we are combining them out of phase with each other. So this is our subtractive or out of phase combination that we get for the antibonding. Alright, and just like atomic orbitals, these molecular orbitals that we form are going to have probability densities. They're going to have regions in space where the electrons are most likely to be found once we combine the atomic orbitals to make these molecular orbitals. And the electron density, the location of that electron density is different between bonding and antibonding orbitals. So in a bonding orbital, you're going to have greater electron density between the nuclei. So it's going to be greater along the direction of the bond, or between the nuclei. So when you populate a bonding orbital with electrons, you're strengthening the bond because you're increasing the electron density between the nucleus. But then antibonding orbitals are the opposite. We have greater electron density outside of the internuclear region. Alright, so we have greater electron density outside the internuclear region, and so when you populate an antibonding orbital with electrons, you're going to start weakening the bond. You're going to start putting electron density outside of where the bond is, which weakens it. And then when you form bonding and antibonding orbitals, whenever we mix two atomic orbitals together, we get one of each. And so one of them is going to be lower in energy than the atomic orbitals, and one of them is going to be higher. We still have to conserve the orbital energy that we started with. And so it's the bonding combination that's lower in energy than the atomic orbitals from which it started, or from which it derives, and then the antibonding is higher than the atomic orbitals. Okay, so that's kind of the general picture of what's happening. So let's look a little bit more detail then at how we mix orbitals together, and let's start with the simplest case, which would be hydrogen, H2, or just mixing two 1s orbitals in general. Alright, so the simplest types of molecular orbital diagrams we're going to talk about are combining 1s orbitals with each other. So only one orbital on each atom. And so what happens when we combine these is, as we said, we get a bonding and an antibonding combination, a bonding and an antibonding orbital. And as we also saw last time, when you have s orbitals, they can only form sigma bonds. So the nomenclature that we used last time, sigma and pi, is still going to be used in molecular orbital theory. That much is still the same. And when we combine s orbitals, you're only going to get sigma bonds. And so the bonding orbital we call sigma, and we put a little subscript 1s to denote that it comes from the 1s atomic orbitals, but it's a sigma orbital. And as we said, the bonding orbital is a sum of two 1s orbitals. It's the additive combination of two 1s orbitals. And like I said, what we're forming here are delocalized molecular orbitals. So we have our two nuclei somewhere there, and the orbital that we form by combining 1s orbitals is going to be delocalized over the entire molecule, and it's going to have a great region of electron density in between the two nuclei, as we said, for a bonding orbital. So this is what the sigma 1s bonding orbital looks like. It's a sigma bond, but it's a single orbital that's delocalized over the entire diatomic molecule. It no longer has separate orbitals at each site that are interacting. And then for the antibonding combination, we call that sigma star, so we put a little asterisk next to it to indicate that it's antibonding. And that's just going to be the subtractive combination of 1s orbitals. And the way that we draw that is we have a 1s orbital of one phase on one of our atoms, and it's going to mix out of phase. And so remember when we were drawing atomic orbitals, we said that there's two different phases for the orbital, which indicate the sign of the wave function. And one of them we draw as a hollow circle, one of them we color in. And so when we want to draw an antibonding orbital, we have two different phases, and we have a node that's in between them. All right, so as I said, this one's bonding, this one's antibonding. And the antibonding orbital, you're doing a subtraction of the two wave functions, so that's the same thing as combining them out of phase with each other, and you get a node that's in between the two nuclei with the electron density outside of the nuclear region. Okay, so that's the difference in the shapes and the pictures of bonding and antibonding orbitals. And then if we want to draw an energy level diagram for this, the way we do this is we're mixing together two 1s orbitals. So we have energy up here on the vertical axis. And as we talked about, when you mix two orbitals together, you get one molecular orbital that's lower in energy. That's our sigma bonding orbital. We can draw dashed lines to indicate that that sigma orbital comes from the mixture of the 1s orbitals. And then up here we get our antibonding sigma star. And for this simple case here, what we see is that we combine two 1s atomic orbitals, we form two molecular orbitals, sigma and sigma star. And in general, as we already talked about, the number of atomic orbitals that you combine is going to be equal to the number of molecular orbitals that you form. Okay? Now I'm giving you a lot of insight and a lot of background into where a lot of these things come from, and some of that, theoretical information is going to be important in some concept questions that you'll have on homeworks and tests. But the reality of the situation is what you mostly need to be aware of is that when you form molecular orbitals, you're going to get sort of this arrangement of molecular orbitals. So for 1s molecular orbitals, you get a sigma 1s and a sigma star 1s. The sigma 1s orbital is lower in energy, the sigma star is higher in energy. And then we need to populate those with the correct number of electrons, depending on what molecule we're talking about, to figure out some of the key features of that. So really, the important part of the molecular orbital diagram is the center part here, which shows you the energy ordering of the molecular orbitals that are formed. These parts on the outside where we're showing the atomic 1s levels, that's just giving you information for where those orbitals are coming from. But the critical part here is the middle, which is what we're going to add electrons to, and then that's going to be related to some of the important properties that we want to talk about. And so before we go into more details on this, let's talk about some of the properties or the parameters that we can determine from molecular orbital diagrams and what we're going to be able to do. So the first thing we're going to talk about is bond order. We know what bond order is in the context of valence bond theory. It's either bond order of 1, 2, or 3. It tells you how many shared electron pairs you have, and it also relates to how strong the bond is. All of that stuff should be reviewed. And from a molecular orbital diagram, once we put the electrons into it, the correct number of electrons, we can also determine the bond order as well. And so there's a relatively simple equation for this. The bond order is going to be 1/2 times the number of bonding electrons, so it's the number of electrons that reside in bonding orbitals, minus the number of antibonding electrons. Okay, so when we put electrons into a bonding orbital, we're strengthening the bond, we're increasing the bond order. When we start putting electrons into antibonding orbitals, we end up weakening the bond, and that's what this equation tells us. All right, and every 2 electrons that we put into a bonding orbital corresponds to 1 bond, which is where the 1/2 comes from. Okay, so once we have the molecular orbital diagram, and once it's populated with electrons, we use this equation to figure out if it's a single, double, triple bond, or something in between those. And then the other thing we can tell from the molecular orbital diagram is what type of bond we have. So the 1s molecular orbital diagram that we started with only has sigma bonds involved. But if we have, as we'll see, when we start doing p orbitals as well, there's going to be pi bonding molecular orbitals as well. And so we can tell whether it's sigma, pi, or some combination that's involved in forming the bond for that molecule. So we get that information. And then, as I sort of started with when I was introducing why we even needed molecular orbital theory, we can also determine the magnetic properties for these molecules. And so once we populate the molecular orbital diagram, we can figure out whether there are unpaired electrons or not, how many unpaired electrons there are, and so on. And so, as we talked about a little bit already, if you have all paired electrons, it's going to be called diamagnetic. So it has no unpaired electrons, and then the property that results is that it's weakly repelled by a magnetic field. And then the other one, which I don't think we've used this term yet, or introduced it formally, is paramagnetic. And in a paramagnetic molecule, you have 1 or more unpaired electrons. And in this case, the molecule would be attracted to your magnetic field. And that's what we saw for liquid O2, that it's stuck right between the 2 magnets that were arranged in that video we showed. Okay, so once you have a correctly filled out molecular orbital diagram, you can predict the magnetic properties, and this was sort of the big early triumph of molecular orbital theory, is that unlike valence bond theory, it did correctly predict magnetic properties for a lot of molecules, and that's why people recognized that it was in some sense superior. So molecular orbital theory is the most accurate and the most decisive bonding theory we have. It's the one that we still use today in modern chemistry research to describe bonding in all kinds of crazy molecules. However, mathematically speaking, it's excessively complicated, so we're only going to be dealing with molecular orbital diagrams of simple diatomic molecules in this course. So we started with H2, we'll see some more about that in a second. And then we'll do things like O2, N2, F2. As I said, just diatomic molecules that we're going to be dealing with for MO theory. All right, so let's start doing it for the simple cases where we mix 2 1s orbitals. And we can also make predictions then about charged species as well, so they don't have to be just neutral molecules that we deal with here. And so if we have H2 plus, we still have 2 hydrogen atoms involved, and we're going to mix together 1s orbitals to form a sigma and a sigma star, just like we did before. So the arrangement of the orbitals is more or less independent of how many electrons we have. If you're mixing 2 1s orbitals together, you're always going to get the same arrangement. But now we have to populate it with the correct number of electrons. And so for H2 plus, hydrogen H2 would have 2 electrons. H2 plus would have 1 fewer than that, or 1 electron. So for H2 plus, a positive cation of H2, we would put 1 electron in, and so that would be our MO diagram there. Just 1 electron. It has to go into the lowest energy orbital first. So all the rules that we learned for atomic orbitals, Aufbau principle, filling lowest to highest, Hund's rule, where you maximize unpaired electrons, all of those still apply here. In this case, we just have 1 electron, so of course it goes into the lowest energy available orbital. And then if we want to calculate the bond order for this, remember, it's 1/2. It's the number of bonding electrons. So in this H2 plus molecule, we have 1 electron in a bonding orbital. It's the only electron we have. You subtract the number of electrons in the anti-bonding orbital. There are none up here. That one's empty. And so this gives us a bond order of 1/2. And this is another difference between molecular orbital theory and valence bond theory. In valence bond theory, we don't really have a good way of ever predicting that we'll have fractional bond orders. We said, bond orders are either 1, 2, or 3. But in molecular orbital theory, when you have an odd number of electrons, it's very common to get bond orders that are fractional, mainly 1/2, 1/2 or 1.5 or something like that. So this predicts a 1/2 bond order, meaning that there's only one electron that's shared in a bond. It's not a typical 2-electron bond, but that prediction is certainly made and certainly true for molecular orbital theory. Now, if we go to neutral H2, we have the same exact orbital diagram. So the two 1s orbitals in hydrogen mix to make a sigma and a sigma star. But in this case, we now have 2 electrons that go into our diagram. So we put both electrons down here. Just like atomic orbitals, each molecular orbital can be occupied by a maximum of 2 electrons. So both of them go into the lowest energy orbital. And then when we calculate the bond order for H2, keep losing that. We still use 1/2. Number of bonding electrons in this case is 2. So both of our electrons are bonding. We still have 0 antibonding electrons. And so this we would predict has a bond order of 1. And if I were to ask you to draw the Lewis structure of H2, I'm sure you would all just draw a single bond between the two hydrogens, which is correct. So in this case, there's no conflict between the two theories. So we predict a single bond for H2. That's what we observe. And that comes directly from the molecular orbital diagram as well. All right, let's keep on going. If we have H2 minus now, or alternatively, we would have the same diagram if we had He2 plus, so 2 heliums with a positive charge or 2 hydrogens with a negative charge. Either of those would have a total of 3 electrons. So you have, for hydrogen, you'd have 2 1s electrons. You'd add 1 more for the negative charge for a total of 3. So if we're putting 3 electrons in this diagram, you have your 1s, you have your sigma star. And so when we put in 3 electrons, the first 2 still go down here, but now we've completely filled the bottom orbital, so we have to put the third one up in the antibonding orbital. Okay, so that's the arrangement that we would get for H2 minus. We will also see on homework assignments and tests especially that you're going to sometimes write electron configurations for molecules using MO theory. So this electron configuration will be written as sigma 1s2, sigma star 1s 1. So that means you have, just like we write for atomic configurations, you write the orbital levels and the number of electrons that are in each one. This has 2 sigma 1s electrons and 1 sigma star 1s. So that's a way of writing that configuration in shorthand. And then from this diagram or from that configuration that we write, we can get the bond order for this. We still have 2 electrons in the bonding orbital, but now we have this one up here that's anti-bonding, and so once again we predict a bond order of 1/2. Okay? So back to a 1/2 bond order. And then finally, when we talk about He2, He2 is going to have 4 electrons because each helium is 1s2 configuration. So now you have a total of 4 electrons when you bring 2 of them together. We talked earlier in the course about noble gases. Helium is the first noble gas, and the idea that noble gases don't tend to make bonds with anything. That's why we call them noble, is that they don't interact with anything, they don't tend to form covalent bonds. But can we use molecular orbital theory to predict whether or not He2 would ever form? And so what we're going to do for this one is, again, we just have 1s atomic orbitals that are going to mix, because all of the valence electrons for helium are in the 1s orbital. There's no other orbitals that we have to consider. And when we mix 1s orbitals, anytime we do that, we get sigma and sigma star. And in this case, we're going to populate these with 4 electrons. So we have to put 2 in the bottom, 2 in the top, putting all 4 electrons in. And so when we calculate the bond order of this guy, 1/2, number of bonding electrons is 2, number of anti-bonding electrons is also 2, we have 2 more up there, and we predict a bond order of 0. Now what does it mean to have a bond order of 0? What it means is that the molecule is unstable and does not exist. So if you fill out a molecular orbital diagram and you predict that the bond order is 0, that means that that molecule doesn't actually exist. And we already talked about how noble gases don't tend to form bonds, and this is why. Because when you try to bond a helium atom to another helium atom, you end up populating both the bonding and the anti-bonding orbitals, and you cancel out the bonding interaction that you would get. So you get a bonding interaction with these 2 electrons, but that's completely canceled out by the anti-bonding interaction from these 2 electrons, and in that you have no bond between the 2 helium atoms. Alright, so that kind of takes us through the simpler cases with just s orbitals, one s orbital specifically. Now let's see what happens when we move on to talk about p orbitals. So we're also going to do diatomic molecules that have electrons, valence electrons in their p orbitals. So the carbon, nitrogen, oxygen, all of those that we've seen. And so how do we mix p orbitals to form molecular orbitals? So p orbitals can also form sigma bonds. We talked about that last time as well in the context of valence bond theory. So if you take two p orbitals that are aligned head-to-head relative to each other and you bring them together, you will form sigma bonding and anti-bonding molecular orbitals as well. So what we're going to assume here, just for the sake of keeping score of all of our p orbitals, is we're going to assume the bond axis is in the x direction. This is not standard, but I think this is how your book does it, which is why I've chosen x. And so if we take two px orbitals, two p orbitals that are aligned along the bond, and we bring them together, that's going to give us sigma molecular orbitals. So the sigma p, it could be 2p, 3p, whatever the p orbitals are that you're mixing, the sigma is going to be the additive combination of those. And so what we want to do here is we want to bring the p orbitals together in phase such that the two phases that are the same overlap with each other. And so we take a p orbital. Remember that p orbitals have a node at the center, and you have two different phases. And your book doesn't really cover that, but I think it's important to understand here when we start combining them to form molecular orbitals. You have this p orbital that has two lobes of that phase. You're going to combine it with another p orbital in the same direction. And if we line up the like phases, so the two unshaded phases combine with each other mathematically, we get an additive combination. And we get a sigma bonding orbital that's going to look something like this. So I'll place the nuclei here so you can see where those are. They're going to be little red dots. So you have nuclei at the center of each of the p orbitals. You have your two nuclei that are interacting. And your sigma p molecular orbital, you're going to get reinforcement between the nuclei when you have these two like phases overlapping. So you get sort of that sigma. You still have the contribution from the other phase, the other lobe of the p orbital that sort of lies outside. That's going to be sort of what your sigma p molecular orbital looks like. It has in-phase overlap in between the two nuclei, just like you would for any sigma bonding orbital. So point being, the pictures might not be terribly important for what you need to know in this course, but when we interact two px orbitals along the direction of the bond, they can overlap to form a sigma orbital. And if you form a sigma orbital, as we said, you also form a sigma star antibonding orbital. So that would be the out-of-phase combination. So that would be taking our first px orbital, combining it out of phase. So this is the in-phase combination. This is the out of phase, which means we're subtracting the two wave functions. Another way to think about an out-of-phase combination is take this second p orbital and flip it over and then combine it with the unlike phases lined up with each other. And so the net result of that is we have our two nuclei, and just like we had for the sigma antibonding orbitals with the s orbitals, sometimes it lags, sorry, we're going to get a node in between the two, and you're going to have unlike phases that are pointing at each other, and then the like phases are going to be arranged outside like that. The opposite phase are going to be arranged outside. So your sigma p antibonding orbital looks like this. You might see different depictions of this in different sources, but the key point being that you have out-of-phase overlap between the two phases that are not alike, and that gives you a node in between the two. So this is what the picture looks like, but again, the key point and the key concept that we want to emphasize is that whenever you mix two atomic orbitals together, you get one bonding and one antibonding. And the bonding will be lower in energy, and the antibonding will be higher. Same story here. This is just sort of a picture of what they look like. As we talked about last time with valence bond theory, p orbitals can also form pi bonds as well. And that's when we have this side-to-side overlap. And so we can make pi molecular orbitals. If we take py orbitals, so if we said that x is the direction of the bond, y would be perpendicular to the bond. Just remember, px, py, and pz are the three different p orbitals that we have available. And so one of your pi-p combinations would be an in-phase combination of two py orbitals, if we put y as the vertical direction on here. So you'd have py, you combine it with another py orbital. and you get a delocalized pi orbital that's, again, it's going to be delocalized over the entire molecule. So you have your two nuclei there, and you're going to have a delocalized pi symmetric orbital that goes over the entire molecule. So it's going to look something like this, where you have electron density above and below the internuclear axis. That's what defines it as pi. You have still the two opposite phases, one above, one below the bond axis. And that's sort of what your pi molecular orbital is going to look like. It's a delocalized orbital with electron density above and below, but still reinforced in between the nuclei, so that would still be considered a bonding interaction. And then if you can form pi bonding orbitals, you can of course form pi antibonding, and that would be the out-of-phase combination of these two. So you'd have a py, and you would combine it in a subtractive sense with another py. And so what that's going to look like is you're going to have your nuclei. You're going to have a node in between them because it's an antibonding orbital. And because the unlike phases are lined up in this case, you get sort of this arrangement. So you're mixing phases that are opposite of each other, and so you get a node in between them. Anytime you mix opposite phases, you create a node in between those two phases. Alright, so that's what you get for so this is your pi p, this is your pi star orbital. Now I've showed this for the y direction, which is vertical. You will have the exact same thing in the z direction with pz. Okay, so pz would be the orbitals that are coming out of the board towards you, and you would get the exact same thing. You would get a pi bonding orbital and a pi antibonding orbital from the combination of the two pz orbitals that are perpendicular to the bond. And so you have two identical sets of orbitals, so you're going to get degenerate pi orbitals. So the pi bonding and anti-bonding levels are each going to have two orbitals associated with them, one in the y direction, one in the z direction, and those two at each level will occur at the same energy. So you're going to have a degenerate set of pi p and a degenerate set of pi star. And when we draw the diagram, that will become more clear. Okay, so in addition to the shapes of the orbitals being different, the other key difference between sigma and pi is that all sigma levels are going to have just a single orbital at that level, but then for pi orbitals you're always going to have two that are at the same energy, one in one direction, one in the other. So that's another difference to keep in mind. Alright, so let's start drawing orbital diagrams for p orbitals. So they're going to look a lot more complicated. I have a template here to help me out so I don't fumble the illustration too bad. Alright, so let's do it for O2. And another thing we're going to see is that there's two different diagrams we have to remember for p block elements. There's going to be this one that I'm showing, which is going to apply to O2, F2, and neon 2. So that would be the second half of the p block. Then there's going to be a slightly different diagram that we're going to use for the first half of the p block, which would be boron, carbon, and nitrogen. Okay, so there's a little bit of a difference there between the two, and we'll get into why that is here in a minute. But when we have O2, remember the valence orbitals for oxygen are 2s and 2p. So each oxygen has a 2s orbital and then a set of three 2p orbitals that we're going to mix together. Okay? And so when we mix the orbitals, the 2s orbitals mix together in exactly the same way as we had for 1s orbitals. You get a sigma 2s at lower energy, and you get a sigma star 2s at higher energy relative to the atomic orbitals. Okay? So that's what happens at the 2s level. That's exactly what we saw before. So these are the individual oxygen atoms that are indicated on the outside. These are the orbitals for O2 in the center. And then when we go to the 2p level, as we just finished talking about, when you mix together 2p orbitals, you can get sigma and pi combinations. And you're going to get both. So if we think about which of these orbitals is going to become lower in energy versus higher in energy, one principle of molecular orbital theory that we didn't really talk about yet, but that is important for this part of the diagram, is that how much the orbitals split in energy is determined by how strongly the two orbitals are interacting with each other. So if there's a really strong interaction between two orbitals, the bonding orbital is going to go way down in energy, the antibonding orbital is going to go way up. If the interaction between the two orbitals is weaker, the bonding orbital is not going to go down as much, and the antibonding is not going to go up as much. There's going to be a smaller gap between them. So if we think about the difference between sigma and pi, remember that sigma is a direct head-to-head overlap, and pi is a side-to-side overlap. So the direct head-to-head overlap is much stronger than the pi overlap. The sigma overlap is stronger than pi, and so that's why you're going to get the sigma orbitals splitting farther apart in energy. So when the two p orbitals mix together, you're going to have the 2px mixing together to make a sigma and a sigma star. And those are going to be split by a larger amount of energy because of the strong interaction that's involved when two orbitals overlap in a sigma fashion. You're also going to get a set of pi orbitals and pi star orbitals, and those are going to split apart not as much, and that's because the pi interactions are weaker. So when you mix those, you're going to get a set of pi 2p orbitals here, and then the antibonding combination up there. So however you want to rationalize it to yourself, this is the order you need to remember for O2, F2, and neon 2. Sigma 2s, sigma star 2s, and then in the 2p level you have sigma, pi, and then pi star and sigma star. That's the order they're always going to come in for this part of the periodic table. Okay? So that's the ordering of the molecular orbital diagram and some of the rationalization for why the p orbitals split in this way. And as we also talked about, at each pi level, there's two orbitals that are at the same energy. So you're mixing together a total of 6 2p orbitals, you get a total of 6 molecular orbitals. Sigma, 2 pi star, 1 sigma star, total of 6. Okay, so that's why we have to remember those details as well. And then finally, if we want to start populating these with electrons, O2 has 12 valence electrons. Each oxygen contributes 6. We know how to count valence electrons by now. And so we're going to fill this diagram with 12 electrons following the rules of the Aufbau principle, going lowest to highest, as well as Hund's rule to maximize unpaired electrons. So for 12 electrons, we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then our last two are going to go 11, 12. We leave those two unpaired because they're going to fill this degenerate set of pi star orbitals, so we put 1 electron in each to maximize the number of unpaired electrons. Okay? And this, I think, reveals the beauty of MO theory. This will predict that O2 is paramagnetic. Alright? Valence bond theory doesn't predict that, but molecular orbital theory does. And this is exactly what is observed experimentally when you do the magnetism studies of O2 that we showed a little video of at the beginning. Alright, and in science, whenever I can't spell sometimes. And in science, whenever the prediction from theory and the experiment match each other, that deserves an explanation point. So that's a pretty cool thing in science when that happens. Okay, so molecular orbital theory predicts paramagnetism for O2, which is what we observe, and that's because of these two unpaired electrons in the pi star molecular orbital. If we calculate the bond order for O2, now we saw at the beginning that valence bond theory predicts that O2 will be a double bond. And what does molecular orbital theory tell us? It's going to be, remember the formula is 1/2 times the number of bonding electrons. We have to figure out how many of these electrons are in bonding orbitals. There's a total of 12 for oxygen. And so we have 1, 2 that are down here in this bonding orbital. We have 2 more, so we have 2, 4, 6, 8. Those 8 electrons are all in bonding orbitals. We have 2 in the sigma 2s, 2 in the sigma 2p, and then 4 in the pi 2p. So we have a total of 8 electrons that are in bonding orbitals. Those are the ones that don't have stars next to them. And if there's 8 that are in bonding orbitals, there should be 4 that are antibonding. The rest of the 12 are antibonding. And so you have these 2 here that are in sigma star 2s, plus these 2 here that are in pi star 2p, a total of 4 electrons that are in antibonding orbitals. And what we get is a bond order of 2. So from the standpoint of bond order, there's no conflict between valence bond theory and molecular orbital theory. We get a bond order of 2 either way. And then finally, if we wanted to write the electron configuration for O2, as you'll often see it in homework questions, this would be, you start at the bottom. So we have sigma 2s, which has 2 electrons in it. Sigma star 2s has 2 electrons. Then sigma 2p, which has 2. pi 2p has a total of 4 electrons. We don't have to write those as individual orbitals. Whenever he says pi, that indicates that you have 2 degenerate orbitals and a maximum of 4 electrons can go in there. And then finally, the last one that's filled is pi star, and that has 2 electrons in it. So this is how we would write out the electron configuration. It doesn't give us all the information directly about paramagnetism and all that stuff, but it does tell us which orbitals have electrons and how many electrons each of those have. And from this configuration, we could predict the bond order if we wanted to as well. All right, so that's how it works for O2. Let's go on and do some of the other ones. Same diagram now for F2. And so F2 has the same exact valence orbitals available, 2s and 2p. And the molecular orbital diagram for F2 is exactly the same as well, in terms of the ordering of the orbitals. So sigma 2s and then sigma star. You have sigma 2p, pi 2p, pi star. Alright, and sigma star. And as I already said for hydrogen, really the only part of this diagram that you have to know is the middle part here, in the order that these sigma and pi orbitals come in. The outside part, as I said, is just a way to show you where those orbitals come from. The sigma 2s orbitals come by mixing 2s orbitals. The sigma 2p and pi 2p come from mixing 2p orbitals. But really, it's the center part of the diagram where you're going to add the electrons to, and that's going to dictate then what the properties of that molecule are. So when we do F2 in this case, now we have 14 valence electrons. Fluorine has 7 each, so a total of 14. And when we add electrons to this one, we get 2, 4, 6, 8, 10, and then we have 11, 12, 13, 14. So in this case, we completely fill the pi star orbital level. And so that means this one is predicted to be diamagnetic. There are no unpaired electrons in this. All of the spin-up electrons have a spin-down electron right next to it, so it's predicted to be diamagnetic. The bond order, you would predict from valence bond theory that F2 is a single bond, and if we calculate the bond order from the molecular orbital diagram, we have 14 electrons. We have 2, 4, 6, 8 that go into the bonding orbitals, and 2 from sigma 2s, 2 from sigma 2p, 4 more from pi 2p. All 8 of those electrons are in bonding orbitals. And then we have 6 electrons that are in antibonding orbitals, 2 electrons from sigma star 2s, and then the 4 electrons that are up here in pi star 2p. All 6 of those are in antibonding orbitals, and so 1/2 times 8 minus 6 is 1, so we predict single bond as well. And then the electron configuration will be written as sigma 2s, sigma star 2s, sigma 2p, all with 2 electrons. Our pi 2p has 2 electrons, and then our pi star 2p also has, 4 electrons each for the pi's. Okay? So we can put a maximum of 4 electrons into the pi and pi star levels, and in this molecule, both of those are completely filled. And we would also predict then that the net bond in this case is a sigma bond, because the sigma and the sigma star 2s cancel each other out. The pi 2p and the pi star 2p are both completely filled, so they cancel each other out. And the only orbital that's left that's not canceled out by an antibonding orbital is sigma 2p. So we would predict that F2 has a sigma bond between the two atoms. That's another little detail that we can get out of this. Alright, and then finally the last one we'll do for this diagram is neon 2, Ne2. Same ordering of orbitals. Now as we introduced for helium, we're kind of familiar with the idea that noble gases don't tend to make bonds with each other. So let's see if that's true for neon as well. So we have sigma and sigma star 2s, sigma 2p, pi 2p, pi star, sigma star. So you want to commit that ordering to memory and be able to reproduce it quickly like I just did. So sigma, pi, pi star, sigma star, those are the important ones. Neon 2, each neon has 8 electrons, so this diagram will get 16 total. And when we do 16, we get 2, 4, 6, 8, 10, 12, 14, 16. Okay, so all of the orbitals get filled when we have Ne2. There are a total of 8 orbitals. There are 16 electrons, so each orbital gets filled completely. If we calculate the bond order for this, out of our 16 electrons, we have 2, 4, 6, 8 that are in bonding orbitals. That's the most you can have for one of these diagrams is 8 bonding electrons. And then how many antibonding electrons we have? We have 2 here, 4, 6, 8 of those as well, the other 8. And so we predict a bond order of 0, which, as we said before, means that the molecule is unstable. Alright, so it's not really meaningful to write an electron configuration for Ne2 because it's not a molecule that even exists. So as we said, if you predict a bond order of 0, that's a way of saying that that molecule just simply doesn't exist. And this is another one where when you try to bond 2 noble gases to each other, that's what's going to happen. Alright, any questions on these diagrams before we introduce one little complication? Alright, so the complication arises when we go to the first half of the P block, boron, carbon, and nitrogen, and try to make and draw microorbital diagrams for these ones. Now, it's not that huge of a complication. So when we have these molecules, we're still talking about the 2p block. So the valence orbitals are still the same, 2s and 2p. So that part doesn't change. But then the ordering of the orbitals changes a little bit. So the 2s level is identical, sigma and sigma star. But the difference is up here in the 2p levels for these elements, the first half of the p block, the pi 2p comes first, and then the sigma. And then the last two are the same, pi star, sigma star. Alright, so I want to highlight that this part of the diagram is the part that changes for these p block elements. So these two orbitals switch order. So B2, C2, N2, which is the P1 through P3 configurations on the periodic table. For those columns of the periodic table, the ordering of the sigma and pi 2p switches. Now that's not the most intuitive thing, because as we talked about when we introduced the previous diagram, we would expect the sigma orbitals to split apart farther in energy and the pi orbitals to be closer together based on the strength of the overlap. So why does the pi come below the sigma here? It's a bit complicated, and not something that we expect you to fully understand, but what ends up happening is that whenever you have sigma orbitals from two different levels, so here we have sigma 2s and sigma 2p, all of the sigma symmetry orbitals can mix together. So it's not just as simple as two orbitals mixing together. What you really get in these molecules is 2s and 2p, those that are along the axis, all mixed together, so you have a much more complicated situation. In the case of O2 and F2, the ones we just did before, the 2s and the 2p orbitals are far apart in energy, so they don't really mix effectively. But for B2, C2, and N2, 2s and 2p atomic orbitals are a little bit closer. Now they're close enough in energy that you get a much more complex mixing that involves 2s and 2p orbitals for the sigma levels. So technically speaking, these sigma levels, especially this sigma star 2s and sigma 2p, that's not really the best abbreviation or the best label for them, because this sigma orbital is going to also include some contribution from the 2s, and this sigma star is also going to include some combination from 2p. So you don't need to know all those details, but that's the reason why the ordering of these two switches. The main thing you have to remember is that that's what happens, and make sure you don't forget that when you're doing the diagrams. Now for some properties, if you don't switch the orbitals correctly, it's okay. You're still going to get the same bond order. But what does change when you don't have these in the correct order is the predicted magnetism, as well as the predicted properties of the bond, whether it's sigma or pi or some combination of those two. So yes?
Why does the top part not switch?
So the top part is, these orbitals are farther away in energy, so they're not going to be influenced by the 2s orbitals. So the only mixing that occurs is with the orbitals that are relatively close to each other, and these antibonding orbitals are so far away from the 2s that they're not strongly influenced by that. So that's a good question, though. So the only ones that switch are the sigma and pi of the bonding orbitals within the 2p section of the diagram. And as I said, that's important sometimes, and I would suggest that you always remember that, but it's really going to only matter if we're asking you about the magnetic properties or the types of bonds that are formed. So if we do B2, the first one in this series, B2 has a total of 6 valence electrons. Each boron is S2P1, so there's a total of 3 for each boron, a total of 6 for the diatomic molecule. And so when we put the 6 electrons in here, we get 1, 2, 3, 4, and then following Hund's rule, 5, 6, we leave those two unpaired. Okay? So the MO diagram predicts that this is paramagnetic, which it is. If we had written the orbitals in the other order, it would have been predicted to be diamagnetic, which is wrong. So we need to have the orbitals in the correct order to correctly predict that it's paramagnetic, which we see. The bond order in this guy. So the number of electrons that are in bonding orbitals, we have the 2 down here and 2 more up here that are all in bonding orbitals. So that's a total of 4. And then we have these 2 electrons that are in the sigma star 2s, so 2 antibonding. And so this is predicted to be a single bond with a configuration of sigma 2s2, sigma star 2s2, and then pi 2p2. Okay, so a total of 6 electrons, and there's 2 in each orbital level that are filled. Now the part about this diagram that's a little bit strange based on things we've talked about before is this is a single bond, has a bond order of 1, but what kind of bond is it? Is it sigma or pi? So look at the diagram. It's pi because we have the sigma 2s's cancel each other out again, and the only filled orbital that's not canceled out by an antibonding combination is the pi level. Okay, so this is a single bond, but it's actually a pi bond, not a sigma bond. And that's something that we would never predict from valence bond theory, but can in fact occur in many cases. Okay, so it's a single bond, but it's pi and not sigma. And that's another prediction from molecular orbital theory that we've never seen before in our simpler bonding theories. All right, that's what we get for B2. If we go one more over to C2, carbon. Now, these are not all stable molecules, I should point out, for various reasons besides their bond order, but you can observe them at least fleetingly, and we can make some predictions about them from the orbital diagram. So C2 has the exact same orbital diagram as B2, 2s and 2p orbitals mixing together, giving us a sigma and a sigma star at the 2s level. And then again, the pi comes first in the 2p level, pi and then sigma. Antibonding are in the normal order, pi star, sigma star. Okay, so that's the order of the orbitals, same exact one as before. In this case, we're doing carbon. Each carbon atom has 4 valence electrons. It's S2P2. It's in group 4 on the periodic table. And so when we do diatomic C2, we're going to have 8 electrons that we need to put in there. And so when we do this, for these 8 electrons, we get 1, 2, 3, 4, 5, 6, 7, 8. So we completely fill the pi 2p level. We still have to follow the rules of lowest energy to highest energy, maximizing unpaired electrons. All of that checks out here. B2 is now predicted to be diamagnetic, which it is. All the electrons are paired in this case. The configuration is sigma 2s2, sigma star 2s2, and then pi 2p4. So that's where the 8 electrons, how they arrange themselves in C2. Bond order for this one. The number of bonding electrons, we have 2 down here, 4, 6. So a total of 6 bonding electrons, 2 in sigma 2s, 4 in pi 2p. And then the other 2 electrons are in the sigma star 2s, so those 2 would get subtracted. And this gives us a bond order of 2. Okay, so C2 is predicted to have a double bond. However, if we look again at the diagram, they're both predicted to be pi bonds in this case. Alright? So in valence bond theory, we would always predict that a double bond is 1 sigma and 1 pi. But for C2, where we invert the order of the sigma and pi orbital levels, we actually get no sigma bonds and 2 pi bonds. Alright, so this is a weird bonding arrangement where the double bond is formed by 2 pi bonds with no sigma bonds in that. Okay? Now, this is maybe a little bit of an oversimplification. As I said, there's a lot of mixing between the sigma and the pi levels. That's what's responsible for the inversion of this ordering here. So in reality, the bonds in these are somewhere between sigma and pi. They're not cleanly classified as one or the other, most likely. But from the simple diagram where we're just apportioning everything as either sigma or pi, this would predict a set of 2 pi bonds and not any sigma bonds. So again, another subtle feature we can talk about. All right, last one is N2. Now, if we draw the Lewis structure for N2, we would predict a triple bond. Let's see if that, and we know that N2 is a stable molecule. It makes up 78% of our atmosphere or something like that. So, it certainly exists in real life. We know a lot about it. So let's see if the molecular orbital theory predicts that it is a triple bond, as we know it is from other analyses. The orbital diagram for N2 is the same as what we've just been working on. Nope, that's wrong. Those are just 2s atomic orbitals. And then 2p atomic orbitals, which we're going to mix together to form molecular orbitals. Again, it's this middle part of the diagram is really the only part that you need. As long as you remember the middle part of the diagram, the finer details are not as important. We get the pi first, and then the sigma up here, pi star, sigma star. Okay. So nitrogen, each nitrogen has 5 valence electrons, so a total of 10 for N2. Counting electrons is exactly the same for molecular orbital theory as it is for Lewis structures. There's no difference there. We just count valence electrons from the periodic table. And then when we put in the electrons, all 10 electrons, we get, skipping, sorry, 1, 2, 3, 4, 5, 6, 7, 8, no, I can't count, 2, 4, 6, 8, 9, 10. Okay, so that's how our 10 go in. So we have, these are always going to be filled, and we have all of our bonding 2p orbitals are filled. Nitrogen is predicted to be diamagnetic, and we saw in the video at the beginning that the liquid nitrogen went right through the magnets, so that's consistent with it being diamagnetic, so the theory and the experiment match up. Bond order, we said we expect it to be a triple bond based on what we know about N2, and if we calculate the bond order from this diagram, we have now 8 electrons in bonding orbitals. That's the most we can have. So our sigma 2s is filled, our pi 2p is filled, our sigma 2p, they're all filled, so that's a total of 8 bonding electrons. And then only 2 of those electrons, the sigma star 2s, are in antibonding orbitals. So out of the 10 total electrons, 8 are in bonding orbitals, 2 are in antibonding, and that combination gives us, we should stop skipping, a bond order of 3, as we would have already predicted. Okay, so we get a triple bond for nitrogen, predicted also from the molecular orbital diagram. And the configuration is sigma 2s2, sigma star 2s, 2, pi 2p4, sigma 2p2. So we've filled all of our bonding orbitals, which maximizes the bond order at 3. So you're never going to get a bond order higher than 3 for any of these compounds. If you calculate a bond order higher than 3, it means you screwed up. There's no long way around that. Okay, so the bond order maximizes at 3 once we've filled all the bonding orbitals, but we have no choice but to also fill one of the antibonding orbitals along with those. Okay? All right, that's N2. The last thing I want to show you, because this is also possible, is we can have fractional bond orders. And we saw that for some of the simpler ones that we did at the very beginning, H2 minus, helium 2 plus, for example, that had fractional bond orders. And we can get the same thing also if we have cations and anions of the main group elements. So if we do N2 plus, we saw that nitrogen has 10 electrons, N2 neutral, so N2 plus would have 1 fewer than that, 9. And so if we arrange the electrons into this orbital diagram, it's still derived from N2, so it's still going to be the same arrangement of orbitals. All right, so same arrangement of orbitals, but this time only 9 electrons go in. And so we stop there. We leave 1 unpaired electron in that last orbital because that's all 9 that we've used. Okay, so we get a sigma 2s2, sigma star 2s2, pi 2p4, and then the only difference is sigma 2p1. Now, if we compare nitrogen N2 neutral to what we have here, N2 plus, we see that the only difference is that we've removed 1 electron from a bonding orbital. So conceptually, we should know then by removing an electron from a bonding orbital, that means the bond should be weaker. Let's see if the bond order reflects that. Bond order is 1/2, and then we have our number of bonding electrons in this case is now 7. 2 down here, 4, 6, 7. We still have 2 antibonding electrons. That didn't change. And so when we get this, we predict a bond order of 2.5. Okay, so we've removed 1 electron from a bonding orbital, which means the bond order goes down, meaning the bond is a little bit weaker. Same thing would have happened if we added 1 extra electron to the antibonding orbital. That would also cause the bond order to go down. So 3 is the maximum bond order, and so if we remove or add any electrons from there, we're going to decrease the bond order each time by a factor of 1/2 each time we add an electron. All right, so that takes us to the end of these MO diagrams for diatomics. Is there anything else that you want me to clarify on this topic before we move on to the last little thing we're going to do? Yep? So this is totally separate from that. Now there are ways to sort of blend together valence bond theory and MO theory for more complicated molecules, but for diatomic molecules, if we're asking you anything about the bonding in a diatomic, O2, N2, whatever, we want you to use molecular orbital theory because that's the one that gives you the accurate predictions. So there are some similarities. If you look at the shapes of some of these orbitals, they are closely related to the hybrid orbitals that we talked about last time, but it's a totally different treatment. The hybrid orbitals are considered as localized on each atom. These ones are considered as delocalized, and the energy levels end up being a lot different for this one as well, which is why you get the different predicted magnetic properties and things of that sort. So they're 2 distinct theories. They are complementary. They're both useful in some sense, but this is the more advanced one, and it's the one that we want you to know how to use just for diatomic molecules only. You can do molecular orbital theory for a lot more complicated things, and if any of you take the other course that I teach, if you make it that far in chemistry, that a large part of that course is dealing with molecular orbital diagrams for all kinds of geometries, but here we're just going to do simple linear diatomics, and that's as complex as we'll get. Now that being said, any other questions before we move on? Sorry. So that's a good point, and that being said, though, we want you to at least qualitatively understand some other things about MO theory. So this is one that you'll talk all about in organic chemistry, and it is introduced in your book, so I want to cover it a little bit. And we said that the key component of molecular orbital theory is that it's a delocalized bonding theory. The orbitals that we form in molecular orbital theory are delocalized over the entire molecule, and that's not necessarily just true for diatomics. Even for larger molecules, you very often have orbitals that are delocalized over the entire structure, and that's very important for some of their properties. So let's talk about an organic molecule, benzene, C6H6. So what you'll learn when you take organic chemistry is that it has this structure. So it's a hexagon of carbon atoms. Pretend that's a hexagon. I'm not used to drawing benzene like that, but this is how I'll draw it so I don't confuse anybody. Just flatten these out a little bit. That should make it better. All right, so it's a hexagonal arrangement of carbon atoms. Each carbon has a hydrogen on it. So it's C6H6, equal numbers of carbon and hydrogen. And it's going to have alternating single and double bonds. Like that, okay? So each carbon has this complete octet, 4 total bonds as we would expect for carbon. What we should recognize, though, is that there's a resonance structure we can draw. So I drew the double bonds at this position, and this position, but why couldn't we shift them all over one? So in reality, this structure is best described by resonance. We don't actually have alternating single and double bonds. We have 6 identical bonds that are in between a single and a double bond. And so the resonance structure for benzene is still the same structure. We don't break any bonds when we do resonance. But what we have is the double bonds are in the opposite location. So instead of being between these 2 carbon atoms, we put the first double bond there, and then they still alternate all the way around. So there are 2 resonance structures to describe this structure. And in reality, the way that this is often drawn is, as we talked about, the bonds are all equal because of resonance. They're not single or double bonds. They're in between single and double bonds. And so the way we often indicate this in benzene is with a circle in the middle to show that those pi electrons are delocalized. So remember, when we do resonance, now that we sort of understand what the difference between sigma and pi bonds are, what we're doing when we draw resonance structures is we're taking these pi bonds and we're moving them around to different parts of the molecule. When we have resonance, we don't move sigma electrons, we move pi electrons. And so these pi electrons are delocalized, so that's often indicated as a circle, showing that there's a set of delocalized electrons that goes around the entire hexagon of benzene. Alright, so all of the carbon-carbon bond distances are equal in length. And if we want to predict the hybridization of these, this is something we talked about last time. So how many electron groups does each carbon have attached to it? Let's look at a single carbon atom. It's bonded to 2 carbons next to it and 1 hydrogen. So each carbon has a total of 3 electron groups, which makes it sp2 hybridized. All right, so that we could have predicted with what we knew last time. Okay, so we have sp2 hybridized carbons, as we would predict from valence bond theory. 3 things bonded to each or attached to each carbon gives us sp2 hybridization. Because of sp2 hybridization, we have one unhybridized p orbital, and that p orbital is involved in forming these delocalized pi bonds at each position. Okay, so that's kind of how the bonding works in this from more of a valence bond approach. Now, if we're considering the sigma and the pi bonds in this molecule, so each of these carbon-carbon bonds involves one sigma bond as well as a delocalized pi bond. So how do we describe that using orbital theories? And so the sigma bonds are best described with valence bond theory, as it turns out. So it doesn't, as I said, these theories are often sort of used in combination, and the sigma bonding in benzene is very easily described with valence bond theory. So we said that each carbon is sp2 hybridized. So at each carbon you're going to have a set of 3 sp2 orbitals. And this is going to test the limits of my artistic abilities here. And those sp2 orbitals are going to overlap to form the sigma bonds. Okay? So remember that in sp2 hybridization you have 3 orbitals that are arranged in a trigonal planar fashion. sp2 correlates with trigonal planar geometry. So those 3 sp2 orbitals are going to be located at each carbon atom, and they're going to overlap with each other to form bonds. Alright, and I didn't mangle that too bad. Now keep in mind, I didn't quite draw the overlap perfectly, but there's overlap here between 2 sp2 orbitals to form a sigma bond there. Overlap, overlap, overlap all the way around. And then the remaining sp2 orbital on carbon is going to overlap with the hydrogen 1s orbital to make the carbon-hydrogen bonds. So you have your hydrogen 1s orbital at each of those positions that's going to overlap with the remaining one to form the bonds with hydrogen. So this is how we can describe the sigma bonding arrangement in this molecule. Using valence bond approach, assume that all of the carbon atoms are sp2 hybridized and that those sp2 orbitals are involved in forming the sigma bonds. That's what we said last time. Remember that whenever you have hybridization, the hybrid orbitals that you have, whether it's sp, sp2, sp3, or anything higher than that, those hybrid orbitals are only involved in forming the sigma bonds. And that's what we can describe here, where each carbon forms 2 sigma bonds with the ones next to it. Each carbon then forms a sigma bond as well with the hydrogen that's located on the outside of the 6-membered ring. And the bond angles in this are all exactly 120 degrees, the exact perfect bond angle that you would want for sp2 hybridization. If you know your geometry from high school, remember that a perfect hexagon has 120 degree angles on it. And so these bond angles between all the carbons are also exactly 120 degrees, as we would expect from sp2 hybridization. So hybridization works well for predicting the sigma bonding, but it doesn't work so well for predicting the pi bonding because the pi bonds are delocalized. And so the delocalized pi bonds are better described with molecular orbital theory. All right, so I put this picture in because I'm not going to be able to draw it. But essentially what's happening here, to give you an idea of how this forms. So we have our hexagon. I'm going to try to draw sort of on its side here. And so each of these positions is a carbon atom, as we said on the hexagon. And if each carbon is sp2 hybridized with 3 sp2 orbitals in the plane of the ring, Each carbon also has an unhybridized p orbital that's going to be perpendicular to that. Okay, so at each position here we have an unhybridized p orbital that's perpendicular to the plane of the ring. And so then each of these p orbitals is going to have side-to-side overlap with the ones next to it, and you're going to get this sort of delocalized overlap between all of the orbitals above and below the plane of your benzene ring. And that's what this picture here from your textbook shows. You have delocalized overlap above and below the plane that's representing the delocalized pi bonding in this molecule. All right? So you're going to form delocalized pi molecular orbitals. And these are going to be formed by overlap of the 2pz, the orbitals that are in the z direction, and the ones that are perpendicular to the xy plane of the molecule. Okay? So that's kind of the general picture. In reality, there's not just one pi molecular orbital. We have 6 p orbitals, so we're going to form 6 pi molecular orbitals. And when you take organic chemistry, you'll learn how all 6 of those arrange themselves in order of energy and how that impacts some of the properties of these molecules. But this just gives you an introduction to the idea that even for larger molecules, you can have these delocalized orbitals that are very important for describing the bonding in a lot of situations. All right, that takes us to the end of today. I will see you guys on Monday. I'll give you a quick recap of the exam results then, and we'll get into Chapter 5 starting then.